Okay, here's the second video in the subject of gases. So in the first one, I kind of introduced pressure, volume, and temperature as three important concepts to kind of think about with respect to gases. Now I want to kind of take it forward to why does that matter? Well, the chapter 5, there's definitely one big takeaway from chapter 5, which is that with there's an equation called the ideal gas equation that allows you to solve really simple problems in terms of, like, if I know how much gas I have, then then can I calculate the pressure? Or if I don't know how much gas I have, but I'm measuring the pressure and the temperature, can I calculate how much gas I have, and that kind of stuff. So this all works, all was based upon some early developments by some scientists in the 19th century that quickly recognized the relationship between pressure and temperature, or the amount of gas and pressure, and these sorts of things. And the laws were Charles, Boyle, and Avogadro all came up with some relationships that the book covers, and I'm essentially to say all of those, when put together, form a much more useful equation called the ideal gas law equation, which is in the book, and you've seen it. It essentially says when you multiply the pressure times the volume, you'll end up with the number of moles of gas times some constant times the absolute temperature of the gas. And so this essentially is a way of saying, if you know, this is a constant R, but if you know 3 out of 4 of the other variables, the volume, the pressure, the amount of gas in moles, and the temperature, if you know 3 out of the 4, you can calculate the fourth one. And typically this is done by measuring volume and measuring temperature, and then you either measure the pressure to figure out how many moles you have, or you know how many moles you have because you've weighed it up front or something like that, and you can calculate how much pressure should result, and that's that sort of thing. I'm not going to do a problem on the video because the problems are covered pretty well in the book, but I want to put this up to talk about a couple of aspects of this. Okay, so first of all, it's important to know that this equation is only true for what is called an ideal gas, basically an unrealistic, well, unrealistic is the wrong word, truly a theoretical gas that actually is similar to many common gases, but only in some scenarios. Okay, so here's what the ideal gas assumes. First of all, the ideal gas equation assumes that that the actual gas molecules have essentially no volume at all, so that the volume of the vessel is completely the volume that's available for the gases. And so it assumes that the actual amount of space taken up by the gas particles themselves is so small that it's insignificant. Okay. Second thing that it assumes is that the amount of empty space that when a gas molecule is traveling through its container, it doesn't encounter other gas molecules. Okay, or if it does, those interactions are negligible. Okay, so essentially it's saying that when a gas molecule is flying around, it's going to continue to fly in a straight line until it hits part of the vessel, and when it hits that, it's going to impart some momentum. It's going to create some pressure on that vessel. Okay, so the ideal gas law assumes that there isn't any wasted energy that's tied up in interactions between gas particles. They actually don't encounter them significantly, and so the momentum will always be imparted on the vessel itself for pressure. Okay, all right. So that's the assumptions. The other thing that you can the other thing that's worth noting here is that the equation actually talks about moles, which of course makes sense somewhat. But in some ways you'd think, well, wait a minute, why moles? Shouldn't it be like the actual mass of the gas? For example, if a gas like helium, which has a molar mass of 2, when compared to a gas like carbon dioxide, which has a molar mass of 44, you'd think, well, if we tried to use this equation on helium and then in one experiment, and then we tried to use this equation on carbon dioxide in another, it doesn't seem right that that we use the same numbers here for helium and carbon dioxide, because carbon dioxide is so much heavier. And you think that the heavier atoms, when they bumped into the walls, they create more pressure, for example, than helium. So that's kind of a curious aspect of this law. The text actually covers this pretty well, and it has to do with the fact that the gas molecules are indeed more energetic, but there's fewer of them in the volume, fewer of them by mass, and so for this reason, the gas law applies equally to gases that differ in molar mass. I'm not sure if I did a great job of explaining that or not, but that's one of the other things I want to point out. We can talk more about that later. The last thing I want to point out is that if you rearrange this equation, you can end up with, I want to make sure I don't blow it, so let me call it up. You can actually arrive at a definition of gas density. Yeah, maybe I should just, I'll do it myself since I can't find it. The number of moles, if you remember, N, is basically equal to the mass of gas divided by the molar mass of the actual compound that we're talking about, the gas. We can rearrange this though and arrive at essentially m over v, which is the mass divided by volume, which is also known as density, is equal to P m molar mass divided by RT. So it essentially says that if, for example, we know a density, or we're trying to calculate a density of the gas, we can easily measure it by measuring the pressure and temperature if we know the molar mass of the compound. Similarly, if there's other things we can do. For example, if we measure the mass and we know the volume, we can actually do some observations of a gas sample and then actually calculate the molar mass, which might give us an idea about what it is. What is this unknown gas? So that's the other thing I want to point out. Now, the other aspect of this course is that densities of gases vary across each other. I mentioned helium and carbon dioxide, for example. Carbon dioxide is a much heavier gas than helium. It actually has a different density at the same pressure and temperature. That's meaningful in meteorological discussions and other situations. And later in a video, I'm going to talk a little bit about atmosphere, about the Earth's atmosphere, and some of the gas compositions. But this is an area that is significant when talking about weather. Okay. Right. So that takes me to those subjects. Maybe I'll end this right now. I will, and I'm going to talk about partial friction next, real gases, and then the Earth's atmosphere in the last video.